there is something orbiting Earth right now that most people have never heard of. Not the moon, not the International Space Station. Something else. Something smaller, stranger, and far more mysterious. A rock that has been quietly circling our planet in near-perfect sync for 60 years, without anyone noticing. Scientists just found it, and when they looked closer, they realized it was not alone. Earth has companions, plural. Objects that travel with us through the solar system in ways that defy easy explanation, that blur the line between moon and asteroid, between visitor and permanent resident. And understanding them opens up a much bigger story. A story about what our solar system actually looks like up close, about the secrets buried in craters and frozen in ice, about geological activity on a world we thought was dead, about structures on other planets that no model predicted, and about the water hidden in the darkest places in our neighborhood that could one day take humans to Mars. Tonight, we are going to cover all of it, the quasi-moons and the mini-moons, the ancient ice at the south pole of the moon, the geological activity that should not be happening on a world 4.5 billion years old, the mysterious flashes of light that have been reported on the lunar surface for 2,000 years, the face on Mars, the hexagon on Saturn, the walnut moon, the magic islands of Titan, and the mission that is going to send humans back to the moon for the first time since 1972, aimed directly at the region where the biggest secrets are buried. Before we go further, if this kind of content is what you come here for, take a moment to subscribe. It helps this channel keep going. Now let us start at the beginning. In 2024, Earth briefly gained a companion. A small rock drifted into our planet's gravitational influence, settled into orbit, made a few laps around us over the course of about 2 months, and then left. Politely. The way a house guest leaves when they sense they have stayed long enough. It slipped back out of Earth's gravitational hold and resumed its journey around the sun, where it had been traveling before our planet briefly interrupted its path. Scientists called it a mini-moon, a temporary satellite, a rock that fell into Earth's gravity well by chance, stayed long enough to count as a moon by most definitions, and then drifted away. These events happen. They are not especially rare. Earth probably picks up 1 or 2 of these temporary companions every year, though we only catch them occasionally because they are small, fast, and extremely dim. But the mini-moon was not the interesting part. The interesting part was what astronomers discovered when they looked more carefully at the space around Earth. Because while the 2024 visitor had been temporary, another object had been quietly keeping pace with our planet for 6 decades. 60 years, without being noticed, without anyone realizing it was there. Scientists designated it 2025 PN7, a quasi-moon, something fundamentally different from a mini-moon, and in some ways stranger. To understand what a quasi-moon is, you have to understand what it is not. It is not orbiting Earth. Not in the way the moon orbits Earth, locked into a path that circles our planet directly. A quasi-moon orbits the sun, but it does so in almost perfect synchrony with Earth, keeping pace with us on our yearly journey around the sun, staying close enough that, from our perspective, it traces lazy loops around our path through space. never getting too far ahead, never falling too far behind, scribbling what looks like slow circles around Earth's position without ever actually being captured by Earth's gravity. Astronomers call this a one-to-one resonance, one orbit around the Sun for every orbit Earth makes. The rock and the planet moving in lockstep, year after year, decade after decade, bound together not by gravity, but by the elegant geometry of their shared trajectory. 2025 N7 is small, about 62 feet across, roughly the length of a bowling lane, small enough to be completely invisible without specialized equipment, which explains why it took 60 years to find. It arrived in its current configuration around 1965 and is expected to maintain its quasi-moon status for approximately another 68 years before the gravitational influence of other planets nudges it off course and it drifts away. Its origins are a mystery. Astronomers have not yet determined its composition. They know its path through space with precision, but they do not know where it came from. Whether it is a piece of the asteroid belt that drifted into this unusual orbit through millions of years of gravitational nudging, or something more surprising. Because some quasi-moons are not from the asteroid belt at all. There is a quasi-moon called Kamo'olawa. It is about 328 feet wide and orbits the Sun in near perfect sync with Earth, just like 2025 N7. But when scientists studied how it reflects light, they found something unexpected. Its reflective properties matched the lunar rocks brought back by the Apollo missions almost exactly. Not just similar, almost identical. The leading hypothesis is that Kamo'olawa is a fragment of the Moon itself. A piece of our natural satellite that was blasted free by an ancient impact entered a stable orbit around the Sun at roughly the same distance as Earth and has been quietly accompanying us ever since. How old is that fragment? Probably somewhere between 1 and 10 million years old, based on estimates of when the impact that formed the Giordano Bruno crater on the Moon occurred. 1 billion years after the Moon formed, something massive hit it, sent debris flying, and some of that debris found its way into this unusual synchronized orbit. And Kamo'olawa is not the only suspect. The temporary mini-moon that came and went in late 2024, designated 2024 PT5, was analyzed carefully. Its surface chemistry looked like lunar basalt, not asteroid material, not comet material, moon material. Another piece of the Moon, visiting briefly before moving on. The picture that emerges is strange and beautiful. Earth is not traveling alone through the solar system. It is accompanied by a retinue of small objects, some temporary visitors, some long-term companions, some possibly fragments of our own Moon returning after millions of years of exile. We have been surrounded by this quiet company for our entire existence as a species, and we only started noticing in the last few decades. These objects belong to a broader category called co-orbitals. Objects that share Earth's orbital path around the Sun, moving in similar trajectories at similar speeds, though not necessarily close to Earth at any given moment. Within this category, scientists distinguish several types, each defined by the specific geometry of its motion relative to Earth. Quasi-moons stay relatively close and trace those lazy loops around our position. Horseshoe orbiters take a very different path. From Earth's perspective, they seem to swing far ahead of us, slow down as they approach a region where our planet would catch up, then drift back behind us before the cycle repeats. If you traced their motion from Earth over a long enough period, the path would form a horseshoe shape, hence the name. Then there are the Trojans. These objects are not just following Earth at a slight distance. They have found something even more stable. Specific points in space where the gravitational forces of Earth and the Sun balance out perfectly. These are called Lagrange points, and they come in 5 varieties. The most important for co-orbital objects are the L4 and L5 points, located 60 degrees ahead of Earth and 60 degrees behind Earth in our orbit. Objects that settle into these Lagrange points can stay there for millions of years without significant gravitational perturbation. Jupiter has thousands of Trojan asteroids locked into its L4 and L5 points, so many that we have given them collective names. Earth has only a handful, but those few have been there for an extraordinarily long time, riding 60 degrees ahead of or behind our planet, invisible to the naked eye, quietly accompanying us on our journey around the Sun. And then there are the tadpole orbiters. Instead of sitting perfectly still in a Lagrange point, they oscillate around it in small, bean-shaped loops. And the jumping Trojans, the most restless of all, which drift between the L4 and L5 positions over thousands of years, unable to settle on one side. Earth has a whole ecosystem of companion objects that most people never think about. Our solar system neighborhood is far more populated and far more dynamic than the simple picture of sun, planets, and occasional asteroid would suggest. We are embedded in a web of gravitational relationships that connects us to dozens of small objects in ways that are still being mapped. And studying them matters, not just scientifically, but practically. Because quasi-moons and mini-moons come close, much closer than typical asteroids, and proximity, in the economics of space exploration, translates directly into cost. To reach an object in the asteroid belt between Mars and Jupiter, a spacecraft has to travel enormous distances against the Sun's gravity, requiring enormous amounts of fuel. To reach a quasi-moon or a captured mini-moon, you need far less. The delta V, the change in velocity required to reach the target, is dramatically lower, which means smaller spacecraft, cheaper missions, and the possibility of human visits. One day, the quasi-moons and mini-moons orbiting near Earth may serve as the first stepping stones of human expansion beyond our planet. Not to live on, they are far too small for that, but to study, to mine for minerals and water, to use as waypoints in the development of space infrastructure. The 62-foot rock that has been quietly keeping pace with Earth since 1965 may eventually be a destination. But before any of that happens, there is a more immediate destination calling, one that has been in view every clear night for the entirety of human history, one that is no longer the simple, solved, well-understood object that most people assume it is. The moon is stranger than you think, not metaphorically, scientifically. The more instruments we point at it, the more data we collect from it, the more samples we bring back from it, the more it surprises us. It has a geological history that is still not fully understood. It has a surface feature that has been confusing scientists for 2,000 years. It has ice in its deepest craters that could rewrite the economics of space exploration. It has geological activity that, by current models, should not be occurring. And it has a companion mystery that we only recently began to solve. A question about what happened to a second moon that some researchers believe once orbited alongside it, billions of years ago. Let us start with the shape of the moon. Not its overall shape, which is roughly spherical, but the distribution of its surface features. Because if you look at the moon carefully, you notice something immediately. The two sides are completely different. The side facing Earth, the near side, is marked by vast dark plains called maria. These are ancient basaltic lava flows that filled enormous impact basins billions of years ago, creating the dark patches that humans have been staring at since before recorded history. The face in the moon, the man in the moon. Whatever pattern you see in those dark areas, it is all ancient lava. The far side of the moon, the side permanently facing away from Earth, is almost entirely covered in ancient, heavily cratered highland terrain. Bright, rough, densely pocked. The maria that define the familiar face of the moon are almost entirely absent. The two sides look so different that the first photographs taken of the far side in 1959 genuinely shocked scientists who had assumed the differences would be modest. They were not modest. They were profound. And explaining them has occupied planetary scientists for decades. The accepted explanation involves the distribution of radioactive elements in the lunar interior. The near side is enriched in a collection of elements called CREEP, an acronym for potassium, rare earth elements, and phosphorus. These elements were the last to solidify as the moon's global magma ocean cooled 4.5 billion years ago, concentrated into the final liquid rock before it froze. And they ended up, for reasons still debated, predominantly on the near side. Radioactive elements generate heat. The near side of the moon has been internally heated by these elements for billions of years, which kept the interior molten longer, which allowed volcanic activity to continue long enough to flood the vast near-side basins with lava. The far side, lacking these heat sources, cooled faster. Its volcanic activity ended earlier. Its craters were never flooded. Its ancient terrain was never resurfaced. But there is a mystery hiding inside this explanation. The South Pole Aitken Basin. The South Pole Aitken Basin is the largest confirmed impact crater in the entire solar system. It sits on the far side of the moon, near the South Pole. It is approximately 1,500 miles wide and up to 5 miles deep, large enough to fit the continental United States inside with room to spare. It formed roughly 4.3 billion years ago, when an asteroid the size of a small country struck the moon at enormous velocity, excavating material from deep within the lunar crust, and possibly from the upper mantle. Given its enormous size and depth, the South Pole Aitken Basin should have been flooded with lava, just like the near-side basins. Its depth would have brought it close to or through the lunar crust, creating pathways for molten rock to well up and fill it. On the near side, that is exactly what happened in similar large basins. It did not happen here. The South Pole Aitken Basin was never fully flooded. Its floor hardened without the extensive lava flooding that created the maria. And the reason, once again, comes down to the creep asymmetry. The far side lacked the radioactive heat sources needed to keep the mantle molten long enough to fill such an enormous basin. The far side cooled. The basin stayed. But the South Pole Aitken Basin holds a deeper mystery. Something that was only detected using precision measurements of the Moon's gravitational field. Something buried beneath its floor that has no complete explanation. NASA's Grail mission, 2 spacecraft that orbited the Moon in precise formation, measuring tiny variations in its gravitational pull, revealed an anomalous mass concentration beneath the basin floor. An object buried in the Moon's mantle, denser than the surrounding material, pulling the basin floor slightly downward. The estimated mass of this buried object is roughly equivalent to 5 times the mass of Hawaii's Big Island. The most compelling explanation is that it is the metallic remnant of the asteroid that created the basin, still embedded in the Moon's mantle 4.3 billion years after the impact. Dense, iron-rich impactor material that sank into the mantle in the aftermath of the collision and never dispersed. The largest impact crater in the solar system may still contain the object that made it, buried 300 miles beneath its floor, measurably altering the Moon's gravity. That object has never been sampled. We know it is there from its gravitational signature. We do not know its precise composition. It sits beyond the reach of any drill or lander we currently have. And the South Pole Aitken Basin has more to offer, because recent analysis has changed what we thought we knew about the impact itself. For years, scientists assumed the asteroid that created the basin came from the south, striking the Moon at an angle that sent the excavated creep-rich material northward, away from the impact site. This assumption shaped how researchers interpreted the distribution of materials around the basin. But when scientists compared the South Pole Aitken Basin to similar large impact structures elsewhere in the solar system, specifically the Hellas Basin on Mars and the Sputnik Basin on Pluto, they noticed something. All 3 have a distinctive teardrop or avocado shape, wide on one side and tapering to a point on the other. And in impact structures like these, the pointed end typically indicates the direction from which the impactor came. For the South Pole Aitken Basin, the teardrop shape points south, which means the impactor came from the north, not the south. The creep-rich material, ejected by the impact, would have been thrown in the opposite direction from what was previously assumed, toward the southern rim rather than the northern rim. This matters enormously because it changes exactly where the most scientifically valuable material ended up. And it turns out that the region now identified as the most creep-rich, the area where the deepest and most ancient lunar material was excavated by the impact and deposited on the surface, is the region targeted by NASA's Artemis 3 mission. The first crewed landing at the Moon's south pole is aimed directly at the most geologically interesting location on the lunar surface. Now, let us talk about the recent discovery that complicated everything we thought we knew about the Moon's geological history. Scientists had long operated under an assumption that seemed well supported by the evidence. The Moon is geologically dead. Its interior had cooled. Its volcanic activity had ended. The seismic instruments left by the Apollo missions recorded some moonquakes, but these were assumed to be caused by tidal stresses from Earth's gravity or thermal expansion from sunlight, not genuine tectonic activity. The Moon was an ancient, frozen, static world. Then researchers from the University of Maryland looked carefully at images of the Moon's far side and found 200 66 ridges that should not be there. These ridges are located in volcanic regions of the far side, areas where lava flows occurred 3.2 to 3.6 billion years ago. The ridges look fresh, much younger than the volcanic terrain that surrounds them. They appear in clusters, typically grouped in sets of 10 to 40, concentrated in areas where the moon's crust is structurally weaker. And when the researchers used crater counting, a standard technique for estimating the age of lunar surfaces based on the density of impact craters, they found something remarkable. Some of these ridges appear to have formed as recently as 200 million years ago. 200 million years ago. That is not ancient history in cosmic terms. It is relatively recent. The dinosaurs were alive on Earth 200 million years ago. If the moon was still deforming its surface that recently, it is potentially still doing so today. The mechanism is the moon's ongoing cooling and contraction. As the moon's interior gradually loses heat, its core shrinks. That shrinkage puts stress on the crust, creating fractures and surface deformations. The ridges found by the Maryland researchers are the surface expression of that ongoing contraction, folds and wrinkles pushed up by the slowly tightening interior beneath. The Apollo seismic data supports this. The instruments left on the lunar surface between 1969 and 1972 recorded 28 moonquakes, ranging from magnitude 1.5 to magnitude 5. These were not the tidal flexing events scientists had expected. They were genuine seismic events consistent with internal geological activity. Some of them occurred in the shallow lunar crust near the surface, in locations that may correspond to regions where the ridges are concentrated. The moon is not dead. It is cooling slowly, contracting gradually, producing surface deformations that are young by geological standards. A world we treated as a static backdrop for 50 years of space exploration may be more dynamic than anyone realized. And the geological activity has implications beyond scientific interest. Future human settlements on the moon, permanent bases designed to support astronauts for months at a time, will need to be built on terrain that is stable enough to support infrastructure. If the moon's surface is still shifting, that changes the engineering requirements significantly. It is one more thing we need to understand before we commit to long-term lunar habitation. Now, let us talk about the lights. For approximately 2,000 years, observers have reported strange transient phenomena on the lunar surface. Brief flashes of light, glowing patches, color changes, reddish or purplish tints appearing on the dark surface and then fading, hazy, cloud-like brightening over craters. Events that last anywhere from a fraction of a second to several hours, appearing without obvious cause and disappearing just as mysteriously. Scientists call them transient lunar phenomena, or TLPs. The historical record contains approximately 3,000 reports of these events, recorded by observers ranging from ancient astronomers to modern professional researchers using high-resolution cameras. They are not fabrications or misidentifications. Something real is happening on the lunar surface. The most famous early report came from astronomer William Herschel on April 19, 1787. He observed a bright glow on the dark portion of the moon that persisted for hours and appeared nearly as bright as the Orion Nebula. Similar events were recorded throughout the 18th and 19th centuries by credible observers using increasingly sophisticated instruments. The question is, what causes them? And the answer, it turns out, is not one thing. It is several different things, each leaving a slightly different signature that scientists are only now learning to read. The shortest TLPs, those lasting less than a minute, are almost certainly impact flashes. The Moon has no atmosphere to burn up incoming meteoroids, so even tiny space rocks reach the surface intact and strike at hypervelocity, converting their kinetic energy to heat and light in a fraction of a second. A meteoroid the mass of a billiard ball can produce a flash visible from Earth. In 1999, during the Leonid meteor shower, scientists captured the first confirmed simultaneous observations of lunar impact, flashes from multiple locations, definitively confirming the impact hypothesis for short TLPs. A 2024 study showed that meteoroids strike the lunar surface more or less evenly across the entire Moon. The apparent clustering of TLPs in certain regions, particularly the large dark plains on the near side, likely reflects where observers have historically pointed their instruments, rather than any genuine concentration of activity. The medium-duration TLPs, those lasting a few minutes, are more interesting. Research published in 2008 and 2009 found evidence that the Moon releases small amounts of gas from its interior, including radon, a radioactive gas produced by the decay of uranium and thorium in the lunar crust. When this gas escapes through fissures in the surface, it can produce a faint glow as it decays, visible from Earth in sensitive instruments. These outgassing events appear preferentially in areas where orbital measurements have already detected elevated radon concentrations, providing a coherent physical explanation for a class of TLPs that had long seemed mysterious. The longest TLPs, those lasting hours, like the Herschel observation from 1787, are explained by a different mechanism entirely. Research from 2012 linked these extended glowing events to interactions between the solar wind and lunar dust. When charged particles from the Sun strike the lunar surface, they can impart an electrostatic charge to fine dust particles, causing them to levitate and form clouds extending up to 60 meters above the surface. These suspended dust clouds can bend or reflect light from nearby sources, creating a diffuse glow that may persist for hours depending on solar wind conditions. 3 different physical mechanisms producing 3 different classes of observable phenomena, all grouped under the same name for 2,000 years, because the observers had no way to distinguish them. The Moon has been trying to tell us something about its interior, its surface processes, and its interaction with the solar system for millennia. We are only now learning to listen. Now let us leave the Moon for a moment and travel to the other side of the solar system. Because our Moon is not the only place in the solar system where strange things are happening. In 1976, the Viking 1 orbiter was photographing the surface of Mars in preparation for future landing missions. It was systematically imaging the terrain, cataloging potential landing sites, mapping the landscape for scientists back on Earth. And in one image from a region called Cydonia, there was a mesa, a flat-topped hill that appeared to have the rough shape of a human face, 2 shadowed indentations that could be eyes. a raised central section that could be a nose, a wide lower feature that could be a mouth. It was, of course, a geological formation shaped by erosion and shadow, and subsequent images taken by more advanced cameras at different sun angles showed it as the natural landform it is. But the face on Mars became one of the most widely discussed images in the history of planetary exploration. A perfect example of the human tendency to find familiar patterns in unfamiliar terrain. This tendency has a name: pareidolia. The brain's automatic pattern recognition system, which evolved to detect faces and other meaningful shapes in the environment, occasionally applies itself too aggressively to ambiguous visual data. A rocky mesa becomes a face. A shadow becomes a figure. Clouds become animals. The brain is, in a sense, too good at finding patterns. The crown face in Libya Montes, another Martian region, the doorway spotted by NASA's Curiosity rover in 2022, the Mickey Mouse shape visible on Mercury's surface. All of these are pareidolia, natural geological formations that happen to trigger the human face detection system. They are not evidence of anything unusual. They are evidence of how our brains work. But Mars does have genuinely unusual structures, ones that are not products of pareidolia, ones that are strange for entirely physical reasons. In recent years, high-resolution images from NASA's Mars Reconnaissance Orbiter revealed 269 spiral-shaped structures in Martian volcanic regions. These are coils of solidified lava, similar in form to lava coils found in volcanic regions on Earth, particularly in Hawaii. They range from 16 to nearly 100 feet wide and are subtle enough that they were only recently detected despite years of orbital imaging. Their significance lies in what they reveal about the debate over Martian geological history. Scientists have long argued about whether the valleys and surface features of Mars were primarily shaped by lava flows or by ice-related processes. These lava coils, similar to structures that only form under specific volcanic conditions, provide strong evidence that extensive lava flow activity occurred in these regions, helping to settle at least some aspects of that long-running debate. And the lava coils are only one of Mars's geological surprises. The planet's surface is a record of processes operating at scales and over timescales that have no parallel on Earth, including impact structures, volcanic provinces, canyon systems, and polar ice caps that together make Mars one of the most geologically complex worlds we know of. Now, let us travel further out, to Saturn. Saturn has been surprising scientists since Galileo first pointed his telescope at it in 1610 and could not figure out what the blurry extensions on either side of the planet's disk actually were. Eventually identified as rings, Saturn's ring system remains one of the most spectacular and scientifically interesting structures in the solar system. But the rings are not the strangest thing about Saturn. The strangest thing is on its north pole. There is a hexagon there, a genuine, persistent, geometric hexagon formed by atmospheric jet streams near Saturn's north pole. It is approximately 9,000 miles across, larger than the diameter of Earth. It has been present since the Voyager mission first photographed it in the 1980s. It persisted through the entire 13-year Cassini mission, which ended in 2017. And it has apparently been there for decades, at minimum, possibly much longer. The hexagon is a standing wave in Saturn's atmosphere, formed by interactions between jet streams moving at different speeds at different latitudes near the pole, under certain conditions, which have been reproduced in laboratory experiments using rotating tanks of fluid. These jet stream interactions can lock into a stable geometric pattern that persists indefinitely. On Saturn, the relevant conditions have apparently maintained a six-sided pattern for decades. Over the course of the Cassini mission, scientists noted that the hexagon changed color. In the early years of Cassini's observations, it appeared distinctly blue. By the later years of the mission, it had shifted toward golden tones. The color change corresponds to seasonal variations in Saturn's atmosphere, specifically changes in the amount of haze produced by sunlight-driven chemistry in the upper atmosphere as Saturn moved through its 29-year orbit, and its north pole transitioned from winter darkness to summer sunlight. A planet-spanning hexagonal storm that changes color with the seasons. Saturn is one of the strangest objects in the solar system to look at, and one of the most fascinating to understand. And then there are Saturn's moons. Iapetus is one of the most visually distinctive objects in the solar system. It is a moon the size of a small planet, roughly 900 miles across, with an extraordinary feature: a ridge that wraps around its equator like a seam on a baseball or the crinkled edge of a walnut. The ridge is approximately 8 to 12 miles high and 124 miles wide in places, stretching around more than 3/4 of the moon's circumference. It is the third largest mountain range in the entire solar system, on an object small enough to fit between New York and Chicago. Nobody knows why it is there. The most developed hypothesis suggests that Iapetus once had a small sub-satellite, a moon of its own. Billions of years ago, some catastrophic event, possibly a large impact, sent material from Iapetus into orbit around itself. That material gradually coalesced into a ring, then a small moonlet. Over time, tidal interactions between Iapetus and its tiny companion began to destabilize the moonlet's orbit. Saturn's gravity, pulling from a distance, eventually disrupted the moonlet entirely. Its debris rained down on Iapetus along the equatorial plane, building the ridge over centuries of gradual accumulation. It is a plausible mechanism. It explains why the ridge follows the equator precisely. It explains the ridge's scale. But it remains a hypothesis, not a confirmed explanation, and the specific details remain contested. Iapetus continues to look like a walnut for reasons we do not fully understand. Titan, Saturn's largest moon and one of the most fascinating objects in the solar system, has its own mysteries. It is the only moon with a thick atmosphere, dense enough that the surface is hidden behind orange haze. It has lakes and seas, but not of water, of liquid methane and ethane. It has weather systems. It has a hydrological cycle, similar in some ways to Earth's water cycle, but operating with completely different chemistry. And on its methane seas, scientists have detected transient, bright features that appear, persist for a time, and then disappear without obvious explanation. They have been named magic islands, partly as a placeholder for the genuine uncertainty about what they are. The leading candidates include several mechanisms, none of them confirmed. Floating chunks of porous water ice that slowly absorb liquid methane until they become dense enough to sink, spending time near the surface as they transition between buoyancy states. Bubbles of nitrogen gas rising from the seafloor as temperatures warm slightly and dissolved gas comes out of solution, similar to carbonation releasing from a shaken drink. waves generated by Titan's slow winds, creating transient reflective surfaces that appear and disappear with changing wind conditions. Each mechanism is physically plausible. Each has complications that prevent it from being definitively confirmed. Titan's chemistry is different enough from anything we have direct experience with on Earth that our physical intuitions do not always transfer cleanly. What the Magic Islands represent, at minimum, is evidence that Titan's seas are dynamic, not static, frozen surfaces, but active environments where physical processes are ongoing, where the sea surface changes over time in ways that depend on temperature, gas content, wind, and the physical properties of the liquid itself. Titan has become one of the highest priority targets for future exploration, not primarily because of the Magic Islands, but because of something more fundamental. It has the chemical ingredients for complex organic chemistry. Its atmosphere is rich in the organic molecules that, on an early Earth-like world, might eventually give rise to biology. The question of whether Titan has anything living in or on it, or whether it represents a snapshot of pre-biological chemistry that could illuminate how life started on Earth, is one of the most important open questions in astrobiology. The Dragonfly mission, a Deitz-eyed rotorcraft lander being developed by NASA, is designed to fly through Titan's atmosphere and explore its surface at multiple locations. If all goes according to schedule, it will arrive at Titan in the 2030s. It may answer some of the questions that the Magic Islands represent, or it may find new ones. Now let us return to the Moon, and to the question that may matter most for the near-term future of human space exploration. There is water on the Moon. This statement, which would have been scientifically controversial 30 years ago, is now established fact. The confirmation came through a series of missions culminating in the L-Cross impact in 2009, when NASA deliberately crashed a rocket stage into a permanently shadowed crater near the Moon's south pole and analyzed the material thrown into sunlight by the explosion. The analysis detected water vapor, water ice, and a variety of organic compounds, including methanol, ethanol, and carbon dioxide, ice in craters at the south pole of the Moon. Ancient, frozen, preserved in darkness for billions of years. The scale of the resource is significant. Estimates based on orbital measurements suggest there could be hundreds of millions of tons of water ice locked in the Moon's polar regions. Some estimates place the total at roughly 1.3 trillion pounds. Not an ocean, but an enormous amount of water by the standards of what a space program would need to operate. To understand why this matters, consider the economics of spaceflight. Every kilogram of material launched from Earth to the Moon requires burning enormous amounts of fuel to escape Earth's gravity. Water is heavy. Carrying enough water for an extended lunar mission from Earth's surface adds dramatically to the cost. If water can be extracted from the Moon itself, the entire economics of lunar exploration change. But water is not just for drinking. Water can be split into hydrogen and oxygen through electrolysis. Hydrogen and oxygen are rocket propellants. A source of water on the Moon means a source of fuel on the Moon. And the Moon, with its gravity only 1/6 of Earth's, requires vastly less fuel to launch from than Earth does. The Saturn V rocket that took Apollo astronauts to the Moon consisted of more than 90% fuel by mass just to escape Earth's atmosphere. launching the same payload from the Moon would require a fraction of that. The Moon, if it has accessible water in sufficient quantities, could function as a refueling station for the entire inner solar system. A depot where spacecraft coming from Earth top off their propellant before continuing to Mars or the asteroid belt. A waypoint that dramatically reduces the cost and complexity of deep space exploration. The resource that makes the solar system reachable rather than merely theoretically accessible. Which is why the permanently shadowed craters at the Moon's south pole have become the most strategically important real estate in the solar system. These craters are extraordinary places. The Moon's axis is tilted only about 1 degree relative to its orbital plane, far less than Earth's 23.5-degree tilt that produces our seasons. The result is that the floors of certain deep craters near the poles never receive direct sunlight. Not seasonally dark, the way polar regions on Earth are, permanently dark. The bottoms of the deepest south polar craters have not seen sunlight since the craters formed, potentially hundreds of millions or billions of years ago. The temperatures in these eternally dark floors are extreme. Measurements from NASA's Lunar Reconnaissance Orbiter have recorded temperatures as low as around -400 degrees Fahrenheit. That is colder than the average surface temperature of Pluto. These craters are among the coldest places in the solar system. In such extreme cold, any volatile material that finds its way into the crater, water ice delivered by ancient comet impacts, for instance, has nowhere to go. It cannot evaporate, it cannot sublimate. It simply stays, frozen, accumulating over billions of years. These craters are cold traps, collecting and preserving volatile materials across geological time. The Shackleton crater is the most famous of these. Over 13 miles wide and more than 2 miles deep, it sits almost exactly at the lunar south pole. Its floor has likely never seen sunlight in its entire history. Whatever ice has accumulated there over the past several billion years is still there, waiting. And the south pole of the Moon has a feature that makes it uniquely suitable for human exploration, despite the challenges of the permanently shadowed craters. Nearby, on the rims and high ridges near the pole, there are peaks that receive sunlight for most of the year. These are called the Peaks of Eternal Light, a name that is poetically apt. While crater floors nearby are frozen in permanent darkness, the highest points around the pole catch sunlight almost continuously. Solar panels placed on these peaks could generate power almost without interruption. A base camp on a sunlit peak, with access roads leading down into the dark craters below, would have both the energy needed to operate and proximity to the ice that makes sustained operations practical. The poles of the Moon are the only places in the solar system where perpetual day and perpetual night exist side by side in close proximity. It is an extraordinary geographical feature of a world that most people think of as a barren, featureless rock. But getting the ice out is not going to be easy. The water in these craters is not a pool or a lake. It is not sheets of ice lying on the surface. It is microscopic crystals mixed into the lunar regolith, the fine-grained soil that covers the Moon's surface. To extract usable water, machines will need to scoop up regolith, heat it to release the water vapor, then capture that vapor before it escapes back into the lunar vacuum. The entire operation must be conducted in total darkness, at temperatures that would disable conventional electronics in minutes, in terrain that has never been mapped from the ground because no light has ever illuminated it. The challenges are significant enough that NASA has developed instruments specifically designed to probe the permanently shadowed craters without entering them. The Lunar Reconnaissance Orbiter carries a suite of instruments that can measure the crater interiors remotely, and the ShadowCam instrument, developed specifically for this purpose, is sensitive to light 100 times dimmer than what human eyes can detect. It can photograph the floors of permanently shadowed craters using only the faint reflected light from crater walls and the lunar sky. These tools have produced the first crude maps of terrain that sunlight has never touched. Rocky, rugged, uneven, navigable by a sufficiently capable rover, but not easily. Future proposals for accessing this terrain range from nuclear-powered rovers equipped with headlights capable of operating in the extreme cold, to rappelling robots that descend crater walls on cables, to drilling systems that could melt their way through frozen regolith and trap the released water vapor. None of these systems exist yet in operational form. But China's Chang'e 7 mission, planned for 2026, will include a flying robot designed to hop into permanently shadowed craters and directly sample the terrain there. If it confirms accessible ice deposits in quantities consistent with the orbital estimates, the case for a permanent lunar South Pole base will become overwhelming. Now let us talk about what is already happening on the Moon and what is about to happen. In 2022, NASA launched Artemis 1, an uncrewed test flight of the Space Launch System rocket and the Orion spacecraft, the systems that will carry astronauts to the Moon. The mission flew the Orion capsule around the Moon on a long, looping trajectory that took it farther from Earth than any crewed spacecraft has traveled since the Apollo era, before returning for a successful ocean splashdown. Every major system performed as expected. Artemis 2 will carry 4 astronauts on a similar trajectory without landing, flying them around the Moon and back. It is planned for 2026. It will be the first time humans have traveled beyond low Earth orbit since the last Apollo mission in 1972. The first time any living person has seen the full disk of Earth from deep space. A rehearsal for everything that comes next. Artemis 3 is the landing. The first crewed lunar surface mission in more than half a century. The target is the South Pole, somewhere in the vicinity of the 9 candidate landing sites NASA has identified near the edge of the permanently shadowed region. The Human Landing System, a modified version of SpaceX's Starship, will carry 2 astronauts from lunar orbit to the surface and back. They are expected to spend approximately a week on the surface, collecting samples, deploying instruments, and conducting the first direct exploration of a region that may contain the ice deposits detected from orbit. If those astronauts find accessible ice, the history of space exploration will take a sharp turn. Every subsequent mission will be easier and cheaper than if they had to bring all their water and fuel from Earth. The South Pole will become the foundation for everything that follows. Following Artemis 3, NASA plans to begin construction of the Lunar Gateway, a small space station in lunar orbit that will serve as a staging point for future surface missions. Rather than traveling from Earth all the way to the surface on each mission, astronauts will dock at Gateway, transfer to a landing vehicle, and descend from there. The Gateway will be assembled in stages over multiple missions, with contributions from international partners, including the European Space Agency, Japan, and Canada. The long-term vision is the establishment of a permanent human presence near the lunar South Pole, a base camp that supports rotating crews, expanding over time from a temporary camp to a facility capable of sustaining human habitation for months. And from there, eventually, the development of the infrastructure needed to support missions to Mars. The Moon is the practice ground. Everything learned about living and working on an airless, low-gravity world with extreme temperatures and high radiation. Everything figured out about extracting resources from the local environment. Everything developed in the way of systems for long-duration surface operations will be applied to Mars. The Moon is close enough to allow regular resupply missions from Earth. Mars is not. Getting Mars right depends on getting the Moon right first. China has parallel plans. Its International Lunar Research Station, developed in partnership with Russia and other nations, targets the same region and the same resources. Two major space powers are both aiming at the same patch of permanently shadowed craters at the Moon's south pole. The competition and cooperation that will unfold over the next 2 decades around this small, cold region of our nearest neighbor will likely shape the course of human expansion into the solar system. And underlying all of it is a question that every Apollo astronaut who spent time on the surface encountered, and that every future lunar explorer will face: the dust. Lunar regolith is one of the most unusual materials on the Moon. Unlike soil on Earth, which has been tumbled and rounded by water and wind over millions of years, lunar regolith consists of sharp, angular fragments at every scale, from boulders to microscopic particles. There is no weathering process on the Moon to smooth these edges. Everything stays jagged. The finest particles, those around 70 microns in diameter, roughly the width of a human hair, are what Apollo astronauts remembered most clearly. Lunar dust gets everywhere. It clings to everything it touches because the angular particles hook onto surfaces at the microscopic scale, and because exposure to solar wind gives the particles an electrostatic charge that makes them adhere aggressively. Apollo astronauts reported that their suits were covered in lunar dust within minutes of surface operations. The dust got inside their landers, fouled their equipment, irritated their eyes and lungs when it was inadvertently inhaled inside the habitat. Several astronauts reported that the dust had a distinctive smell when it first entered the oxygen-rich cabin atmosphere, likening it to burnt gunpowder or the smell after fireworks. The sharp dust particles reacting instantly with oxygen after billions of years in the vacuum of space, producing combustion-like chemistry on contact. Future lunar missions will need to address the dust problem in ways that Apollo never needed to, because future missions will be longer. Dust management, filtration systems, suit cleaning procedures, and the development of dust-tolerant equipment are significant engineering challenges for any sustained lunar presence. There is also a challenge related to launch and landing. Every rocket that lands on or launches from the Moon kicks up a significant plume of regolith. The low lunar gravity and the absence of atmosphere mean that this ejected material travels far and fast. A rocket landing near a lunar base could shower it with high-velocity regolith, sand-blasting solar panels, damaging equipment, and creating a collision hazard for other spacecraft in the vicinity. As lunar operations scale up and multiple spacecraft begin making regular visits to the same region, the management of regolith disturbance becomes a significant operational concern. These are not insurmountable problems. They are engineering challenges with known solutions. But they are part of the full picture of what it actually means to operate on the Moon for extended periods. A picture that the Apollo missions gave us only a glimpse of. Now, let us take a step back and look at the full picture of what we have covered tonight. Because when you lay it all out together, a theme emerges. The solar system is stranger and more dynamic than the simplified picture most people carry around. It is not just a sun surrounded by planets orbiting in clean, well-separated tracks, with everything predictable and static. It is full of unexpected structures, ongoing processes, unresolved mysteries, and objects that do not fit the categories we have built to describe them. Earth travels with a retinue of companion objects that most people never think about. Some of them possibly fragments of our own moon that have been orbiting the sun near us for millions of years. The moon itself has ongoing geological activity, an unexplained magnetic record, ancient ice in its darkest craters, and a geological target that may reveal more about the earliest history of the solar system than any previous mission has approached. Mars has geological formations shaped by processes that we are only beginning to understand. A face that is not a face, a door that is not a door, and evidence of a volcanic history far more complex than the simple picture of an extinct geological world. Saturn has a hexagonal storm larger than Earth that has been there since we first photographed it, and that changes color with the seasons. Its moon, Iapetus, has a ridge that should not exist under any fully confirmed model. Its moon Titan has seas of liquid methane with transient surface features that physicists cannot fully explain. And underneath all of it is a more fundamental realization. We have been exploring the solar system seriously for only about 65 years. We have detailed data on a handful of objects. We have landed on only 2, the Moon and Mars. Everything we know about the rest is based on flybys, orbital imaging, remote sensing, and the occasional atmospheric probe. Every time we look more carefully at a place we thought we understood, we find something we did not expect. The Moon's geological activity, the magnetic ribbon found by the Interstellar Boundary Explorer, the magic islands of Titan, the quasi-moon that has been silently keeping pace with Earth for 60 years. The solar system is not a collection of solved problems. It is a collection of partially answered questions, each answer revealing 3 more questions behind it. And in the coming decades, more answers are coming. Artemis will put humans on the south pole of the Moon and may confirm the ice deposits that could transform space exploration. Chang'e 7 will send a robot into the darkness of a permanently shadowed crater. Dragonfly will fly through the orange skies of Titan. Future missions will characterize the quasi-moons and mini-moons that share our orbital space. New telescopes and new instruments will find structures and phenomena we have not yet imagined. The solar system has been around for 4.5 billion years. We have been seriously looking at it for less than 1/1,000,000th of that time. We are at the very beginning of understanding what is out there. One view is one person. One mission is one step. And every step reveals a universe that is larger, stranger, and more intricate than the one we thought we were standing in. We are just beginning to look. But before we talk about where we are going, we need to talk about what would happen if the moon simply were not there. Because the moon is not just a companion. It is not just a landmark in the night sky or a destination for future missions. It is an active participant in everything that happens on Earth. A gravitational partner that has been shaping the conditions for life on this planet since long before the first cell divided in the first ocean. Remove the moon from the sky, and Earth becomes a different planet. Not immediately. Not in ways you would notice in a single human lifetime. But over thousands and millions of years, the absence of the moon would alter Earth in ways that cut to the heart of whether complex life could exist here at all. Start with the tides. The moon's gravity pulls on Earth's oceans, creating the tidal bulges that produce the rise and fall of sea level that coastal regions experience twice daily. This is familiar. What is less familiar is the full scope of what tidal forcing does to a planet. The tidal interaction between Earth and moon is not a one-way relationship. Earth's gravity raises tides on the moon too, though the moon has no liquid ocean for those tides to manifest in. The tidal forces are instead expressed as stresses in the moon's rocky crust. And those stresses, over billions of years, have had a profound effect on both bodies. The moon is gradually moving away from Earth. Every year, the moon drifts approximately 1.5 inches farther from our planet. The mechanism is tidal locking and tidal friction. As Earth rotates beneath the tidal bulge that the moon raises in the oceans, the bulge is carried slightly ahead of the direct Earth-Moon line by Earth's rotation. This displaced bulge exerts a small gravitational pull on the moon, accelerating it slightly in its orbit. In response, the moon gains orbital energy and moves to a slightly higher, slightly larger orbit. The process will continue until Earth's rotation slows to match the moon's orbital period, at which point the system will be tidally locked and both bodies will face each other with the same face permanently. That will not happen for billions of years. But the gradual recession of the moon has been going on since the beginning. Early in Earth's history, the moon was much closer. The tides were enormously more powerful. The oceans sloshed with regularity and violence that dwarfs anything experienced today. The energy dissipated by those ancient tides was substantial. It heated the oceans. It contributed to mixing nutrients and minerals throughout the water column. It may have played a role in creating the conditions in which life first emerged. The tides also slow Earth's rotation. The friction of ocean tides against coastlines and the sea floor dissipates energy, and that energy comes from Earth's rotational kinetic energy. Earth is gradually spinning down. 4 billion years ago, a day on Earth was approximately 6 hours long. The moon's tidal breaking has lengthened the day to 24 hours over geological time, and it continues to lengthen it by about 1.4 milliseconds per century. A faster rotating Earth in the distant past had a different climate, different atmospheric circulation patterns, different ocean currents. The interaction between day length and climate is complex, but it is real, and the moon has been the primary driver of the change. Now consider the moon's effect on Earth's axial tilt. Earth's rotation axis is tilted approximately 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is what produces the seasons. During northern summer, the northern hemisphere is tilted toward the Sun, receiving more direct sunlight and experiencing warmer temperatures. During northern winter, the northern hemisphere is tilted away, receiving less direct light and experiencing cooler temperatures. Without tilt, there would be no seasons. Every latitude would receive the same amount of solar energy year-round. But the tilt does not stay fixed. Earth wobbles. On timescales of tens of thousands of years, Earth's axial tilt oscillates between roughly 22 and 24.5 degrees. This oscillation, driven by the gravitational influence of the other planets in the solar system, changes the intensity of the seasons. When the tilt is higher, summers are warmer and winters are colder. When it is lower, the differences between seasons are reduced. These changes in axial tilt are one of the key drivers of Earth's ice age cycles. When the tilt and other orbital parameters align in certain ways, the northern hemisphere receives less summer sunlight. Snow accumulates year over year. Ice sheets expand, and an ice age begins. The most recent ice age peaked about 20,000 years ago, when ice sheets covered much of North America and Europe. The cycles of ice ages and warm periods that have characterized Earth's climate for the past several million years are driven significantly by these orbital and axial variations. But Earth's tilt oscillates only within a relatively narrow range, between 22 and 24.5 degrees. Mars, which has no large moon, has a much less stable axial tilt. Mars wobbles between approximately 10 and 60 degrees over millions of years, driven by the gravitational perturbations of the other planets without a large stabilizing moon to dampen the oscillation. At 10 degrees, Mars's poles would be permanently shadowed and cold. At 60 degrees, the poles would point nearly toward the Sun for part of the year, baking in continuous sunlight for months, while the equatorial regions were in darkness. A Mars with a 60-degree axial tilt would have a radically different climate than it does today. The ice at the poles would sublimate into the atmosphere. Weather patterns would be dramatically different. The surface would be reshaped by different wind regimes and temperature distributions. Earth, by contrast, has been relatively stable for billions of years. Its axial tilt has wandered only 2.5 degrees in either direction, a small variation in geological terms. The seasons have remained recognizable. The climate has changed dramatically over Earth's history. Yes, but the changes have been constrained. The extreme swings that would have come from an unstable tilt have been damped out by the moon's gravitational steadying influence. Some researchers have argued that the moon's stabilization of Earth's axial tilt was a necessary precondition for complex life. Life requires time to evolve. Complex, multicellular life requires hundreds of millions of years. If Earth's climate had been as chaotic as Mars's climate might be without a large, stabilizing moon, the repeated disruptions might have reset the evolutionary clock too many times for complexity to accumulate. This is a contested claim. Other researchers point out that life on Earth is resilient and that some level of climate variability may actually accelerate evolution by providing new selective pressures. The question of whether the moon was strictly necessary for life on Earth is not settled. But the question of whether the moon has influenced the conditions for life is not in doubt. It has, profoundly and continuously, for 4.5 billion years. Now, consider the Moon as a shield. The inner solar system is not empty. It is populated by a continuous flux of asteroids and comets, objects ranging from specks of dust to bodies hundreds of kilometers across, moving on orbits that periodically cross the orbits of the inner planets. Earth has been struck by large impactors throughout its history. The impact that killed the non-avian dinosaurs 66 million years ago was caused by an object approximately 10 kilometers across. Larger impacts occurred in the more distant past. The Moon itself bears witness to the early bombardment history of the inner solar system in its heavily cratered surface. The Moon acts as a partial shield. Its gravity attracts and intercepts some of the objects that would otherwise strike Earth. The Moon's cratered surface is a record of impacts that the Moon absorbed on Earth's behalf, in addition to impacts that Earth also received during the same periods. How significant this shielding effect has been over geological time is a matter of ongoing study. Jupiter plays a much larger role as a gravitational shield for the inner solar system, its enormous mass deflecting and capturing objects that might otherwise reach the terrestrial planets. But the Moon's contribution is real. More visibly, the Moon provides Earth's nights with a source of light that has shaped the behavior of life on Earth in ways that are still being discovered. The cycle of lunar phases, from new moon to full moon and back over 29.5 days, has been woven into the biological rhythms of countless species. Coral spawning on the Great Barrier Reef is timed to the lunar cycle with extraordinary precision. Many marine invertebrates synchronize their reproductive behavior to the phases of the Moon. The tidal cycles driven by the Moon have created unique intertidal ecosystems, zones between the sea and the land that are alternately submerged and exposed, home to organisms adapted to the challenging conditions of that rhythmically changing environment. Intertidal zones are scientifically significant beyond their ecological diversity. They are thought to have been one of the key environments where life first began the transition from ocean to land, hundreds of millions of years ago. The regular exposure and flooding of the tidal zone created the conditions for organisms to evolve tolerance for terrestrial conditions while remaining close to the water they needed. Without tides, without the intertidal zone, the history of life's move onto land might have been profoundly different. The Moon has shaped Earth's climate, slowed its rotation, stabilized its axis, contributed to its tidal ecology, and partly shielded it from impacts. It has been a partner in the history of life on this planet in ways that no other single object has matched. And we are now preparing to visit it again, not to plant flags and leave, but to stay. The Moon that Apollo astronauts visited in the 6 missions between 1969 and 1972 was the Moon as we understood it then. A geologically quiet, well-characterized, airless rock with nothing left to surprise us. The Moon of 2025 is different, geologically active in ways we did not know, rich in ice resources we did not confirm until 2009, still generating transient light phenomena that 2,000 years of observation have not fully explained, accompanied by a retinue of companion objects, some of them possibly lunar fragments, that we are only beginning to catalogue. The Moon that the Artemis astronauts will visit is a stranger richer, more complex world than the one their predecessors walked on. And the questions they will be trying to answer are bigger. Not just what is the moon made of, but what can its resources tell us about the history of the solar system? Not just where does the ice come from, but can we use it to build the infrastructure for human expansion into deep space? Not just what are these ridges and why are they there, but is the moon still geologically active today? And if so, what does that mean for where we build? The solar system is not done surprising us. The moon is not done surprising us. And we are not done exploring. The next chapter is just beginning, and for the first time in half a century, it involves people. But to understand where we are going, it helps to understand where we came from. And the moon's origin story is one of the most violent and extraordinary events in the history of the solar system. The moon did not always exist. There was a time, early in Earth's history, when our planet orbited the sun alone. No moon in the sky. No tides of the magnitude we know today. No stabilizing influence on the axial tilt. Just a young, molten, geologically violent planet making its way through a solar system still crowded with the leftover debris of planetary formation. Then something hit it. The giant impact hypothesis, which has been the dominant model for the moon's origin for several decades, proposes that approximately 4.5 billion years ago, a Mars-sized protoplanet collided with the young Earth. This body, which scientists have named Theia, struck Earth at a relatively low angle and at a velocity somewhat above the mutual escape velocity of the two objects. The collision was not a direct head-on impact. It was more of a grazing blow, energetic enough to be catastrophic, but not so violent as to simply disintegrate both bodies. The result was the most dramatic event in Earth's history. The outer layers of both Theia and Earth were vaporized, ejected into space as a vast cloud of superheated rock vapor and molten droplets. The iron cores of both bodies merged, sinking together into what became the new, larger Earth. And the ejected material, a vast disk of debris surrounding the proto-Earth, gradually coalesced under gravity into the moon. The evidence for this model comes from multiple directions. The moon's bulk composition is similar to Earth's mantle, suggesting it formed from material that had already undergone the kind of differentiation that Earth's interior experienced. The moon is depleted in iron relative to Earth, consistent with the model in which the iron cores of both bodies merged rather than contributing to the lunar material. The isotopic composition of lunar rocks, particularly the ratios of oxygen isotopes, is essentially identical to Earth's, suggesting that the moon is made of the same material as Earth, mixed thoroughly by the collision. The moon formed hot. Immediately after the giant impact, the entire body was molten, covered in a global magma ocean hundreds of kilometers deep. The outer layers were liquid rock. In this state, as the magma ocean slowly cooled over millions of years, different minerals crystallized at different times. Lighter minerals floated upward, forming the bright, ancient highland crust that dominates the lunar surface today. Denser minerals sank, forming the mantle. The iron and nickel that remained after the core merged with Earth's settled into the small lunar core, which is proportionally much smaller than Earth's. In the final stages of the magma ocean's crystallization, the last remaining liquid was enriched in all the elements that did not fit into the crystal structures of the minerals that had already solidified. These were the creep elements, the potassium, rare earth elements, and phosphorus that would eventually end up concentrated in the near side, the chemical fingerprint of the moon's unusual cooling history. The moon formed close to Earth. In the immediate aftermath of the giant impact, the newly formed moon orbited at a distance of perhaps 14,000 miles, compared to its current distance of 240,000 miles. At that proximity, the tidal forces between Earth and Moon were enormous. Earth's gravity raised tidal bulges in the Moon's still cooling magma ocean, thousands of times larger than the ocean tides of today. The Moon's gravity raised titanic tides in Earth's global magma ocean. Both bodies were being flexed and heated by each other's gravity during the critical period of their early cooling. As the Moon gradually receded, driven by the same tidal energy transfer that continues today at a much slower rate, the intensity of the tidal heating decreased. Both bodies cooled more rapidly as they moved apart. Within a few 100 million years, the Moon had solidified its crust. Its volcanic activity had begun to slow, and its surface had begun to record the relentless bombardment of the late heavy bombardment period, when the orbital rearrangement of the giant planets sent a flood of asteroids through the inner solar system. The Moon we see today, ancient and cratered and geologically quieter than it once was, is the record of all of that history preserved in rock and dust and permanently shadowed ice. But here is where the story gets strange again, because some researchers believe the giant impact did not produce just one moon. The two-moon hypothesis proposes that the debris disk that formed after the giant impact coalesced into two objects, not one: a primary moon of familiar size and a smaller companion moon, approximately 1/3 the diameter of the primary. This smaller companion settled into a stable orbit alongside the primary, the two objects orbiting Earth together for approximately 80 million years. Then the smaller moon was destroyed. Not in a violent, high-energy collision that would have left an obvious crater and mixed the two bodies thoroughly. Instead, the researchers who developed this hypothesis propose that the smaller moon eventually moved onto a path that brought it into a slow-motion collision with the primary. A merger at low relative velocity, somewhere around 3 to 4 times the speed of sound, fast enough to spread the smaller body across the primary's surface, but too slow to excavate a basin or produce a large, symmetric crater. The smaller moon, in this model, essentially smeared itself across the far side of the larger moon. Its material added to the far side's crust, thickening it, contributing to the highland terrain, building up the rough and heavily cratered landscape that Luna 3 photographed in 1959, and that has puzzled scientists ever since. This hypothesis provides a potential explanation for one of the most enduring mysteries in lunar science. Why are the two sides of the moon so different? The giant impact model and the subsequent magma ocean crystallization explain many things, but they do not naturally produce a moon, where one hemisphere has thick highland crust and the other has thin crust flooded with volcanic plains. The two-moon hypothesis offers a mechanism. The far side's extra material came from a second, smaller moon that was incorporated into the primary long after both had formed. The hypothesis is consistent with the available evidence. the far side crust is thicker. The composition of the far side terrain is consistent with what you would expect if it had received additional material from a body with a similar bulk composition to the primary moon. Computer simulations of the merger process can reproduce the observed crustal thickness asymmetry, but it is not confirmed. It is a model, not an established fact. The evidence is consistent with it, but the evidence is also consistent with other explanations. Confirming or ruling it out requires exactly the kind of direct geological investigation that the Artemis missions are being designed to conduct. The south polar region of the Moon, where the Artemis 3 landing is targeted, is on the edge of the South Pole Aitken Basin, the largest impact structure in the solar system. Rocks excavated from deep within the Moon by that enormous impact 4.3 billion years ago have been scattered across the south polar region. When Artemis astronauts collect samples from this area, they will be picking up material that came from the deep lunar interior, material that may carry the chemical signatures of the Moon's formation and earliest evolution. If those samples show evidence of a compositional distinction between the near side and far side mantle material, if they preserve the isotopic or mineralogical fingerprints of material that originated from a separate body before merging with the primary moon, the two-moon hypothesis will gain significant support. If the samples are compositionally indistinguishable from near-side material, the hypothesis will be weakened. The south pole of the Moon is not just a source of ice for future missions. It is a geological archive of the solar system's earliest history. The rocks there have not been resurfaced or chemically processed by volcanic activity the way the near-side rocks have been. They retain the record of the Moon's violent birth and early evolution in ways that no other accessible location on the Moon does. This is why the South Pole is the target, not just for practical reasons related to ice and sunlight, but because it is the place where the oldest and deepest secrets of the Moon are most accessible from the surface. Now consider what the Moon's formation means for Earth specifically. The giant impact that created the Moon almost certainly also changed Earth fundamentally. The collision brought together Earth and Theia, and the merged Earth that emerged from the impact was different from the Earth that existed before. The iron cores merged, creating a larger, more energetic dynamo in Earth's interior that generates the magnetic field that protects Earth's surface from the solar wind. Without a sufficiently strong magnetic field, the solar wind would strip away Earth's atmosphere over geological time, the way it stripped away Mars's atmosphere after Mars's own dynamo shut down billions of years ago. Whether Earth's magnetic field would have been strong enough to protect the atmosphere without the enhancement from the Theia merger is uncertain. But the Moon's formation is intimately connected to Earth's ability to retain its atmosphere, and an Earth without an atmosphere is an Earth that cannot support complex surface life. The Moon's formation may also have contributed to Earth's water supply. Some researchers have proposed that the giant impact delivered material to Earth from Theia that was richer in certain volatile elements, including water. The precise water budget of the early Earth is one of the most contested questions in planetary science, partly because so much of what we think we know is based on models rather than direct evidence. But the connection between the Moon's formation and Earth's habitability runs deeper than just tidal stabilization. We formed together. Earth and Moon are a system, not two separate objects that happen to orbit a common center of mass. They formed from the same catastrophic event. They have been gravitationally coupled ever since. They have influenced each other's evolution continuously for 4.5 billion years. The habitability of Earth and the geological history of the Moon are not independent stories. They are the same story, told from two different perspectives. And now, for the first time in more than half a century, we are preparing to visit the Moon, not as tourists taking a brief look around, but as explorers intending to stay. The science behind that decision is everything we have discussed tonight. The ice that could sustain a permanent presence. The geological activity that makes the surface a dynamic environment rather than a static rock. The ancient material near the South Pole that preserves the record of the solar system's first chapter. The quasi-moons and mini-moons that tell us about the broader family of objects that accompany Earth through the solar system. The Moon is not just a destination. It is a laboratory, a resource depot, a historical archive, and a gravitational partner that has shaped the conditions for life on Earth since before the first organism breathed oxygen into our atmosphere. Everything about it is more interesting than it looks from the ground. And we are finally going back to find out how much more interesting it is than we currently know. The investigation continues. The Moon is waiting, and what we find when we return will rewrite what we know about where we came from, what makes a planet habitable, and how far into the solar system the conditions for complex life can extend. One mission at a time, one sample at a time, one discovery at a time. We are just beginning. There is one more thing worth sitting with before we close. Something that connects every thread we have followed tonight into a single, larger picture. We started with a rock that has been quietly accompanying Earth for 60 years without anyone noticing. A 62-foot piece of something, possibly a fragment of our own moon, traveling in near-perfect synchrony with our planet on its annual journey around the sun. Small, dim, invisible without specialized equipment, undetected for 6 decades despite orbiting in our neighborhood continuously. That detail, the idea that something real and scientifically significant could be right next to us for 60 years without being noticed, is a theme that runs through everything we covered tonight. The Moon has been showing us transient light phenomena for 2,000 years. Flashes and glows and color changes that observers recorded dutifully across centuries without being able to explain them. We only recently developed the combination of theory, instrumentation, and accumulated data needed to begin understanding what those lights actually are. Meteorite impacts, radon outgassing, electrostatic dust levitation. 3 different physical processes producing 3 different classes of phenomena, all hiding in plain sight in the records of generations of astronomers who noted them down and wondered. The Moon has had geological ridges forming on its far side within the last 200 million years. The seismic instruments left by Apollo recorded moonquakes that suggested ongoing interior activity. And yet for decades, the consensus was that the Moon was geologically dead. The evidence was there. The interpretation was wrong. The Moon has had water ice locked in its permanently shadowed craters for potentially billions of years. Every time a spacecraft has flown over the South Pole with sensitive instruments, the signal has been there. We confirmed it definitively in 2009. For all the years before that, the ice was there, waiting. The moon formed from the same catastrophic event that changed Earth forever, and the two bodies have been in continuous gravitational conversation for 4.5 billion years, shaping each other's evolution, influencing the conditions for life, leaving fingerprints of their shared history in the composition of rocks we have barely begun to sample. What this pattern suggests is that the solar system is not something we understand well. We understand it approximately. We understand the broad outlines, the obvious features, the things that are large enough and bright enough and close enough to be detected with the tools we have had. But beneath those broad outlines, in the permanently shadowed craters and the far side ridges, and the 62-foot companions nobody noticed for 60 years, there are layers of detail and complexity that we are only beginning to access. Every new instrument reveals something the old instruments missed. Every new mission finds something the orbital surveys did not show. Every new analysis of old data, like the reinterpretation of the South Pole Aitken impact direction, changes what we thought we knew. This is not a failure of science. It is the nature of exploration at the frontier. The solar system is large and complex and old. We have been exploring it seriously for about 65 years, with increasingly capable tools. What we have found in those 65 years has already rewritten textbooks multiple times. What we will find in the next 65 years will rewrite them again. The Artemis missions will bring humans to the south pole of the moon and may confirm the ice resource that changes the economics of space exploration. They will collect samples from the oldest and deepest accessible geological record on the moon. They will deploy instruments that will monitor the geological activity we now know is ongoing. They will lay the groundwork for the permanent human presence that eventually leads to Mars. Chang'e 7 will send a robot into the darkness of a permanently shadowed crater and may return the first direct samples of ancient lunar ice. Dragonfly will fly through Titan's orange skies and measure the organic chemistry in its methane lakes and dunes. Future missions to Europa, Jupiter's ice-covered ocean moon, will search for signs of life in the liquid water beneath kilometers of ice. Other missions will characterize the quasi-moons and mini-moons that share our orbital neighborhood. And somewhere in all of that exploration, there will be discoveries that nobody predicted. Structures that do not fit current models. Phenomena that generate new questions faster than they answer old ones. Objects that have been there all along, invisible because we were not yet looking in the right way. The solar system is not a museum of solved problems. It is a living system, still evolving, still surprising, still full of things we have not yet seen. The 62-foot rock that has been quietly keeping pace with Earth since 1965 is not the last thing we will discover in our immediate neighborhood. It is a reminder that the neighborhood is larger and more populated and more interesting than the simple picture suggests. That even in the most familiar parts of the solar system, the parts we have been observing for centuries with improving instruments, there are things we have missed. There always have been. There always will be. And finding them, one instrument and one mission, and one unexpected discovery at a time, is what exploration is for. The solar system is not done with us.